Hello and welcome to another session of the Digital WE Days. My name is Tom and I will moderate this webinar today. The topic of today is signal integrity analysis on NRZ and PAM signals. Yeah, very warm welcome to our speaker today, Nick Lebas. He is from Rode and Schwarz and he will hold the presentation today. Very cool to have you here, Nick, today. High-speed digital systems demand clean signals and precise analysis, but how do techniques like PAM, equalization, and eye diagrams help maintain signal integrity? So let's take a closer look. Stage is yours, Nick. Have fun.
Hello, and welcome to this presentation on signal integrity analysis on NRZ, non-return to zero, and PAM, Pulse Amplitude Modulator signals. My name is Nick Lebas, oscilloscope product specialist coming out of the UK. And the main motivation for this is that NRZ is sort of been around for a very long time, whereas pulse amplitude modulator signals are now becoming more prevalent. The reason for this is because of bandwidth limitations within channels. Essentially, you would like more bandwidth coming out of your Ethernet DRAM devices. And so to acquire more data, especially in the era of AI, we are then having to shift to try and shift more data through the same channel. So you can see here a little bit of an explanation behind non-return to zero. This is essentially bits are defined by only two levels, 0 and 1. And it doesn't return to zero, so it normally goes to a positive and negative voltage, whereas pulse amplitude modulated signals, they then have different levels so that we can put multiple bits on each level. So running through a little bit of the agenda that we're going to go through. So I will briefly introduce to you signal integrity. We will then move into eye diagrams, what they are and why they're useful, and also have a bit of a demo. And you'll see that there'll be a theme of going through demos, and we'll be focusing mainly on the demo aspects so that you can see what it is that you can do with an oscilloscope and the practicality of these things. We'll then move on to a bit more of an advanced topic, so equalization and embedding. And then finally, we'll move on to PAM analysis, which is sort of the echelon of what we're trying to achieve today. So moving into what is signal integrity. So signal integrity is the term used to define the quality of a signal. So if we have a look at the transmitter side here, we can see that coming out from this chip, we have an ideal sort of non-return to zero signal. And just through the medium of a channel and vias going through to the receiver on the other end, we can see that we have distortions. And this is what we're trying to measure. This is what we're trying to define, look at, and identify where the issues are coming from. So there's quite a few reasons why these common problems might occur. There might be certain transmitter effects that we're trying to look out for, so rise and fall imbalances, timing jitter, so this is in line with the clock that is running through at the same point, whether this is an embedded or a parallel system. We then look at channel-related effects, so this is the ringing that you might see on top of the waveform, signal loss and attenuation, perhaps due to the channel, crosstalk from nearby channels or nearby electronics, and the reflections due to impedance mismatches. Now, this is a key one that normally catches people out. And then obviously external sources, so EMI being a big component of that, and other noise from other networks around the system. So this is what we would look out for. Now, one of the tools that we can use that's very useful is an eye diagram. Now, an eye diagram is a very useful graphical tool that we can use to essentially take a lot of data and have a look at the signal integrity of it. So how an eye diagram is made is typically we have a reference clock, and we trigger off this reference clock, and we have the data. And we essentially, as the data comes in and the reference clock is triggering, we can then overlay these data to create an eye diagram. We can then put in a mask, and then we can create a test where we can then look at and create boundaries for where we'd like the test of amplitude or horizontal displacement to occur. So interpreting an eye diagram, so we have different things that we can take away from the eye diagram. So looking at the jitter, so this is the horizontal crossover that we see to the left and right of the eye. We then have the noise on the top, so the peak to peak and the standard deviation. And then we also want to look at the eye width and eye height, so that these are how open the eye is, how we can perceive the eye. So these are all very important. What you need, and what we've just glossed over quite quickly, is the reference clock for an eye diagram. So typically, if you have access to the clock from your serial bus data, then you can use that as your trigger event to then recreate the eye. But in terms of embedded systems, so looking at perhaps USB or DDR, the clock is embedded inside. So we need something to recover that clock from that data. And this is where the clock data recovery, or CDR, becomes paramount. Now, there are different types of CDR and different types of clock. We briefly in a second, we'll go through and have a look at what the differences are between these different types of clock data recovery. But essentially what we're trying to do is recover that data and see how it looks in different ways. So now that we've looked at the theoretical part of what an eye diagram is, let's look at the practical aspect of actually generating these types of eyes and showing it on an oscilloscope. So now let's look at what an eye diagram looks like. Here I have a USB 3.1 device, and I'm essentially going in through channel 1 and channel 3. So if we look at the screen, we can see that I have a very nice signal of positive and negative from the USB device. And essentially the first step that I want to do here is quickly change this into a differential signal. So I have channel 1, channel 3. For the keen-eyed of you, you could do this typically within math as well, but this is a way of doing it through hardware on this scope in particular. So here we can see very clearly our data signal, the ones and zeros. So I want to show you the first type of eye, and this is what we call the advanced eye, or software CDR eye. So what I'm going to quickly do is go in through here, and essentially the first step that we want to go for is to set up the actual signal within the signal configuration. So we will define our source, differential 1, our standard, so you can see there's different types of technologies here, USB, it snaps to USB 2, and we can say USB 3.2 Gen 1, and you can see that it's given us the correct symbol rate of 5 gigabaud per second. So you can see a signal flow diagram down here. Now, later on in the presentation, we'll talk through a little bit more about the embedding and equalization and some of the more advanced features here. But we're going to jump in and jump straight to the eye analysis right away. We're going to define our source, differential 1. And you can see in here that we have CDR, so clock data recovery, as our preferred reference signal. As you can see, clock could be another one if we had access to that, if it wasn't part of this embedded system. And we'll double check that the software CDR will change it to differential 1. And you can see it's copied over the 5 gigabaud per second in there. So we then have the correct data rate. So if I then click on, you can start to see that we have an eye diagram. And what I want to do is reduce the amount of data that we have at the top here, so that we have maybe just a couple of edges here. So we can now see behind that we have 3 edges, and we see that we're starting to build up the eye diagram. Now this is in reference to a clock. So if I quickly create an equation with the software CDR that we've just defined, and we can see our clock right there. You can see, let's put it into a separate box. So we then have our clock to the left here, our data to the right, and as we give it more edges, more data, we can see that we're slowly generating the eye around it, and we can start to really see, well, an eye diagram be built from this, and then we could then put in masks, and we can start to make sort of thresholds around this. Now this is what we call the software CDR, because this is done in post-processing. So not necessarily the fastest, we have to give it a certain acquisition time, a certain period of time that we want to then measure between. It's not necessarily the fastest, but it does give us sort of the amount of data that we can then utilize. The other one that we want to look at real quick is the hardware CDR, which is what we call the live eye. So what I will do is I will just get rid of my eye diagram, get rid of my clock, and I can change my trigger to differential 1, and you can see that we have a CDR there, and this will then be done in the hardware. So this will actually be in line with the scope, and what it essentially will do is reprogram the FPGA so that the hardware CDR is in line with the trigger system, essentially giving us the trigger speed or the trigger rate that we can possibly have on the scope itself. So here we can see it's up and running. We then can give it the data. It's quite zoomed out, again from our previous one. So let's zoom in, and as we zoom in, we can see our eye diagram generate. And then this is what we call the live eye. So this means that it's constantly acquiring with this scope, having a trigger rate of up to 750,000 triggers per second. So this means that any glitches or spurs can then be captured. You can still put the mask in there and capture anything that might occur at random times or at fluctuating events. So these are the two differences of CDR. So now let's look at embedding and equalization and the theory behind that. So we're going back to the same sort of transmitter and receiver system, and we're looking back at the transmitter. So here we're now representing via an eye diagram, and what we can do now is through the channel we can do something called embedding. You might have heard of de-embedding, where we try to remove artifacts from the front end of the scope. Embedding is that we're now trying to simulate. So here we can see maybe even a short and long channel versions of the eye diagram that we've now purposely caused attenuation, jitter to occur inside of it so that we can simulate what we could do in the real world. And then back at the receiver side, we then have something called equalization, which we can then reopen the eye again through different types. So you can see in the receiver side, we have CTLE, which is continuous time linear equalization, FFE, which is feed forward equalization, and DFE, which is decision feedback equalization. And then you might have even seen on the transmitter side that we also have some equalization that can be done there, which is FFE again, but this is then a type of pre-distortion where we can try and anticipate the distortion that would happen within the channel and then cause additional behaviors on the front end to then add extra, rising edge on top of it so that we can inhibit and displace what the effect would be through the channel. And then this is not just something that we can do on the scope, this is something that is done within different serial bus communications. So this is the USB 3 Gen 1 and 2 USB standard. And here we can see at the transmitter side that within the USB standard, there is some equalization that is done from the chip and also at the receiver side as well. So you can see, and typically within these standards, they define what types of equalization are required from these different serial protocol buses. So you can then play around with and see what the receiver would eventually see on the other end through these networks of these serial bus communications. So having a little bit of a look more into embedding. Now these are typically something that we can then characterize ourselves. So we can take cables, wires, and we can measure them with a VNA, and we can then simulate these types of mediums through the scope using S parameter files, typically 2 or 4 port, and we can then see the response and see the effect that these have to our signal before then maybe doing some equalization on the other end. And then if we look a little bit further into equalization as well, this is typically a way to combat what we call intersymbol interference. So this is when you might have quick transitions from ones and zeros, and essentially because of these quick transitions, they can then cause it not to quite get to the level of 0 or not quite to get to the level 1 and can cause distortions. And so this is what we're seeing here. We can see that with this middle image in the center, we have our ideal one and then what we're actually measuring. And then we can essentially pull those highs and lows and levels of this PAM4 signal so that we can actually get the definitive levels that we're looking for so that the receiver can understand what it is it's being spoken to about. So now that we've talked about embedding and equalization, let's have a look at how we can do this on the oscilloscope. So here we have, again, the advanced eye, looking at that software CDR. And if I go back to the signal configuration, we can see we have our setup of the USB 3.2 Gen 1 at 5 gigabaud. Now we have a little bit more focus now on the signal flow overview. So we can see de-embedding. This is essentially counteracting anything from the front end of the scope, so cables, fixtures, things like that, so that we can then account for amplitude issues or any frequency discrepancies so that we can use that with S parameters. We then move into embedding and equalization. So clicking on that, we can then see a very similar diagram to what we saw earlier, where we have the transmitter size, so TX FFE, the embedding, so the medium in which we are trying to travel through, and then the equalization at the end, so the receiver side of it. So what we can do, let's have a look at embedding. Now, within embedding, we can then simulate different types of whether cables, fixtures, anything custom. What is really good about the USB organization is that they provide these S parameters for free online on their website. So we can go in here, we can see that we already have some of them within it. See that I can put in the S4P file and it gives us the actual response curves that we have on the side here. So we can check S31, check that it's going down, enable this, make sure it's all cascading, turn it on. We can see our response, we can see the step response and the magnitude response. This looks good. And then what we can do is we can turn on lane 1. And let's put this over here. Let's do an acquisition. And so we can see the data that we have here. And we can already see straight away that it's already attenuated via the amplitude. We can see that in comparison to the differential signal we have above, that is already attenuated. So let's have a look at what this would look like within an eye diagram. So let's go to our eye analysis. Let's generate another eye. This time lane 2, we will match the same CDR, so differential 1, 5DR. Perfect. This overlays it. So let's just put it below. And now we can see the effect that we're now simulating within the channel. And we can see from lane 1, from the idealized signal that we have at the front, we are now adding attenuation plus some jitter based on the channel that we're simulating. So this is really good. So what we want to then do next is do some equalization. So going back into embedding, we'll generate another embedding file. We will just mirror the exact attenuation that we're doing. And I'm doing this so that in comparison, we can see the effect that this does. So turning that on, we then can go into the equalization setting. So this setup, we can then see the different types. So we have CTLE, that's the continuous time linear equalization, FFE, the feed forward equalizer, and then DFE, decision feedback equalization. Now, within the USB standard, it tells you which ones to use. So I know for a fact that's CTLE and DFE. So we'll start with the CTLE. And you can see straight away it's recognized the standard. We're going to do a long channel. If you then go into the actual settings themselves, we can see we have the 0 frequency and the pole frequencies. Now, when you look into the standard itself, it gives you these values. And essentially, what we have here is a starter frequency of 650 megahertz. We're trying to amplify the frequencies at 1.95 gigahertz, the speed of the data bus. And then we're going to quickly attenuate anything above that. And this is a way of only focusing on the signal details that matter to the serial bus. And so we can turn this on, go back to our setup, turn on, and finally turn lane 2 on. And we can put that just below lane 1. We can see that there's not much of an amplitude jump, but you can see that there is a difference between lane 1 and lane 2. So let's generate the third and final eye. And we'll just simply go to lane 2, make sure it's the same CDR. Perfect. Generate that, and we'll just put it into the bottom there. And so we can see that we've now reopened the eye. We've now accounted for some of the jitter discrepancies that we saw. We could go further, look at DFE. That one requires a CDR. But these are the different tools that you can utilize to eventually see what the receiver would see on the other side. So this is a very useful tool to use when you are evaluating the signal integrity of your system. So now that we've looked at embedding and equalization, let's go to the final step and look at PAM signals and looking at eye diagrams here. So here I have an Ethernet 100 base T signal just going into our Ethernet test fixture. And what I want to do is, again, start right at the beginning, go into our signal configuration. I want to change the differential very quickly just before I do that. Reduce the call mode, then go back into signal configuration. We'll then define that as differential 1, Ethernet, and then we have 100 base T. It's already defined the PAM order of 3. So before we had USB 3.1, and that was a PAM order of 2 technically. So non-return to 0 is a PAM order of 2 steps. We then could go up to PAM 8, but this is a PAM 3, and it's already defined the 125 megabit per second. So again, we have the same signal flow overview. You know, we could do some de-embedding, we could do some embedding and equalization, but let's jump straight to the eye analysis. We'll change our source to differential 1. The CDR will already be checked and changed to 125 megabaud. And we can then enable our software eye here. We have a few edges. You can see that we can give it a bit more data. And we start to fill in this PAM order level 3. Now, with the PAM eye, there are a couple of things that you can additionally do. Now, obviously, this is becoming more complex. We now have multiple eyes on different levels. So we want to isolate and have a look at different levels, different transitions between them. So let's go back in to the eye analysis. We can then look at the filter characteristics, and we can see that we have different things that we can look at. So we have the whole eye. We can look at specific eyes. So if we want to look at certain level transitions between level 0 and 1, or 1 and 2. So then we can highlight and have a look at what transitions lead to that one. Or we can then select different eyes as well, depending on our analysis. And we can even select the top and bottom thresholds. But because this is Ethernet, there are no transitions that will happen from the top echelon to the bottom one. So this, to me, is now correct. And I've already done a little bit of analysis on it. So this shows you how you could do this. You could then go further, like we showed earlier, just going into embedding and equalization. I mean, looking at the signal configuration, we can see de-embedding, embedding, equalization. At the eye analysis, we then would move into measurements. There is advanced jitter and noise, which I've been skirting around. Actually, Pasi Soanen last year did a very good presentation doing a bit more in-depth detail into jitter analysis and the other things that you can also pull away from them. So I'd very much recommend to go back to last year's oscilloscope days and have a look at Pasi's if you want a bit more detail. So now that we've looked at embedding and equalization and PAM eye on the oscilloscope, this brings me to the end of my presentation. Hopefully you found it very useful and insightful about how you make an eye diagram and the different things you can do for your analysis. Thank you very much for watching.
Yeah, thank you, Nick, for the interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from Nick's presentation. And then So now you can download it on the black button. So Nick, are you ready for the questions?
I am very ready.
Perfect, cool. Then we can start the session. First question. What are some best practices for designing circuits that utilize NRZ and PAM signaling to ensure optimal signal integrity?
Well, yes, that's a very good question. Obviously, we've done quite a lot of analysis within this presentation. So, how do we actually sort of what the best practices for this? I guess one thing that we kind of glossed over was utilizing and actually looking at sort of the traces that obviously that propagate the waveform through, and with that, we could look at things like reflections, impedance mismatches inside of that. You essentially want to have a continuous impedance all across the line. The one thing that we also didn't quite look at as well is the sort of transmitter side of equalization, and you could do some pre-emphasis and essentially increase the sort of amplitude a little bit of your signal so that it propagates through, depending on the length of the line. So there are, and there's quite a lot more as well within that question. I think it's very open-ended, but hopefully that gives you a little bit of an idea. We could use something like a VNA as well to kind of look at the traces in a bit more depth.
Cool, thank you, Nick, for the answer. Then we will come directly to the next question. So, Nick, do you see a good question in the chat? Then you can tell me that. But we're not.
I believe the next one down looks quite good. Looking at the chat.
Yeah. Then this question: what effect does signal amplitude have on signal integrity? What is the typical differential signal amplitude for Ethernet lines?
So yes, for signal amplitude on signal integrity, I mean, we saw the eye diagram, and if the amplitude obviously is lower, then it's going to be really hard to define or realize the eye and really understand your data coming through it. You'd imagine that through a very long trace, and sort of one thing you can sort of simulate this is adding an extra cable, should we say, to reduce down the amplitude. You can see that as it gets smaller and smaller, it becomes even more sort of noisy and harder to realize. So this is where, having good amplitude is incredibly important. Then the typical differential signal amplitude for Ethernet lines, I think it was roughly around 200 millivolts plus or minus that we saw on that PAM3 signal, but it may depend on the Ethernet standard that you're working on as well.
Okay, cool. Thank you. Then, next question. I hope this was a good question for you, Nick, live. What about phase shift in data lines as compared to ref clock in signal system? Is there any option to identify and measure that?
So I guess this is maybe a slightly different question. I mean, my interpretation of it is that sort of the phase shift in data lines, I'm guessing, is the variability that you're kind of seeing in the horizontal system, and this is typically what we define as jitter, having a phase shift that, I guess, in reference to that clock, and we're sort of expecting the data line to also be directly on it, or the rising edge of or the falling edge of the data line, and having any kind of phase shift to that is then defined as our jitter, or as our horizontal jitter. And this is where you might want to do either a manual measurement, or if you're looking at the eye diagram, that sort of horizontal crossover point, that is then also your jitter definition as well, and you can do various measurements around that to have a little bit more detail within it.
Okay, thanks. Then I would say one last question. Yeah,
a few more are popping up.
yeah. Okay. Next question. You highlighted it in channel-related effects that reflections due to impedance mismatches was a key common problem. How can I determine or measure the impedance mismatch for an A?
So yes, impedance mismatches are very can be quite a big problem within signal integrity. A VNA would be something that would be able to also look at this problem, to look at the actual scatter parameters within a channel. And the RTP that I was working on also has a sort of pulse source as well that could also be used for something called a TDR and TDT measurement, which is something taken from sort of VNA capabilities, which are time domain reflection and time domain transmission measurements. And essentially you can look at a trace, a cable, and see how this pulse would then be reflected back, and you can then see if any impedance mismatches along the way that might cause signal integrity problems for you. So this is where, yes, a VNA is normally a very complementary piece of kit with your signal integrity needs on top of utilizing a scope.
Okay, thank you. Then I see one more question. Does Rode and Schwarz scope provide an option to extract touchstone model of cables? USB, Ethernet, yeah,
etc. I'm not entirely sure what is meant by touchstone model, but I assume this is kind of relating to the sort of S parameter files of the actual unit itself. Now, we do have some predefined fixtures and cables within the system itself that if you wanted to de-embed or embed back into your signal integrity S parameters, I just see he's written S parameters, yes. That can be defined, but then again, this is kind of relating to the VNA being a very complementary unit that you could then characterize your own fixtures, cables, etc., that you could then account for and either de-embed or embed back into the system. So the answer is yes, to some extent, but then if there's a lot of things out there that could be characterized and used in these types of signal integrity. So you can also characterize your own, especially if you're doing custom fixtures and custom cables.
Thank you. Then I would say we are finished with the session. Thank you, Nick, for the interesting presentation and for all the answers, and also for your time. Yeah, at the participants, thank you for joining. Oh, sorry, Nick. Do you want to say something?
No. It's a real pleasure to be on these digital WE days. Seen a lot of very good presentations on here, so hope to sort of stick around for the next couple of days myself as well.
Very cool. Thank you. Then, thank you for joining. Hopefully, we see us on our next session. Tomorrow, we had a Rode and Schwarz session at the same time, so hopefully, we see us with just now, and stay tuned. Bye-bye.